Hello everyone, welcome back to my general chemistry mini lecture. Today we will talk about the thermochemistry calculation. And this is a very common question in this topic. It will ask you calculate the total energy to heat up an ice from low temperature and then melt and then boil to the steam and also heat the steam to higher temperature than the boiling point. So you need to calculate the total energy needed. Okay, so this to heat the heat of those physical state change. This is called heat of fusion. That means this is when the ice melt to water, the amount of energy needed, okay, per gram. And this is called heat of vaporization, and that is the energy consumed when the water boiled, so from liquid to gas. And this CS is a specific heat capacity. And we have a three physical states, so we have a three CS. CS of ice, CS of water, CS of steam. Okay, so to solve this question, there are 5 steps. So you need to calculate 5 steps heat. So before we do the calculation, first we need to explain the physical change here, step by step. First, we have this. It's actually heating curve. The axis X is heat added, and the y-axis is the temperature increase. And we have the initial temperature of the ice is 21 degree, but negative, so it's at minus 21 degree. It's cold. It's basically the temperature of the freezer. Okay, so it's negative 21 degree, and then if you heat the ice, it will increase the temperature, and then until 0 degree, which is the melting point of ice. So this diagonal in this heating curve means temperature change, but no physical state change. So it's in this whole diagonal, or you can say slope, it's all ice, the solid state of water. Now, when it at 0 degree, when you keep heating it, that will melt. When the ice melt, the temperature will be 0 degree, will not be changed. And then this is called melting. And during this melting, you need to consume energy. That energy is called heat of fusion. And then after all ice melt to liquid water, if you keep adding heat, then the water will increase temperature. And during this diagonal change, this is another slope, that's another temperature change, but no physical state change. So that's all liquid water here until the temperature reached the boiling point. For water, it's 100 degrees Celsius. So, and then if you keep adding heat, then the water will boil, converting from liquid to gas. And during this step, the heat is the heat of vaporization. Okay, that's the number 2260 joule per gram. And then when all the liquid water boiled or evaporate to gas, then the temperature still keep 100 degree. Okay, so and then this is boiling. When you keep adding heat to the steam, the temperature also increase. And then that step is another slope here. So that physical state will not be changed, but the temperature will change. So that's a steam. And the question asks you calculate until the temperature reach 130 degrees Celsius. So I will just write this. You can keep adding to increase temperature more. So this is the called heating curve. Okay, so to summarize it, so when you see this diagonal or slope here or here, that's temperature change, but no physical state change. When you see the plateau here or here, they have physical state change, either melting or boiling, but no temperature change. Okay, so melt at melting point, boil at boiling point. Now let's calculate the heat. We have two formula to calculate the heat. First, at the slope, the formula, the heat equals mass times specific heat capacity of that substance, and then times delta T. Delta T is the temperature change, so it's the final temperature minus initial temperature. To calculate the heat of the plateau, that is mass times heat. If it's the heat of melting, that's mass times heat of fusion. If you calculate the heat of boiling, that's mass times heat of vaporization. Okay, so we have 5 steps here. First, second, third, fourth, fifth step. So we need to calculate each step's heat, okay, consumed. So first, let's look at this step. This step is the diagonal, the slope, the mass times specific heat of ice. We have that available, and delta T. Delta T is the final 0 minus initial negative 21. Okay, that's the delta T. So now you can calculate this first step. The heat absorbed is 1580. Okay, the mass is given 36. This is the specific heat of capacity of ice. So now, first step, we got the heat consumed. Second step is the plateau, so we need to use this heat equation. So mass times specific heat of fusion. So mass is 36. Heat of fusion is 334. So we calculate you need 12,024 joule to melt this 36 grams ice. And then this third step, another slope. Okay, so you need to use the mass 36 times the specific heat capacity of water, that's a 4.18, and then temperature change, that is 100 minus 0, so it's 100 actually. So that is 15,048 joule to increase the water from 0 degree to 100 degree. Another step is another plateau boiling. You need to use the mass times heat of vaporization, 36 times 2,260. You get 81,360 joule to boil the 36 grams water. And then last step, you heat the steam from 100 degree to 130 degree Celsius. So you have to use the slope, this formula, because it is diagonal slope. So that is mass times specific heat capacity times delta T. Mass is the same. The CS of steam is 2.01 here, and the temperature change is 130 minus 100. So that's basically 30. So you calculate that 2,171 joule. So what will be the overall heat consumed? Just addition of Q1, Q2, Q3, Q4, Q5. Add them together. So you add them together, the 5 heat consumed together is 112,183 joule. So usually people use kilojoule because it will give you a more reasonable number here. So divide by 1,000, then you can get 112.183 kilojoule. So that's a more common unit, okay, for this heat. Okay, this is a very, very common question in this topic, and I will give you some more example of calculation. Okay, here is the common maybe question every day. Probably you have common sense about this, right? How many ice cubes to make iced tea? So if you have a cup of tea, which is about 65 milliliter, it's a small cup, and 85 degrees Celsius, pretty hot. and the density of tea is 1.008 grams per milliliter. It's a little slightly higher than water. And then single ice cube, it's about 15 grams, and the temperature is negative 18 degree, okay, Celsius in freezer. Specific heat capacity of ice is given 2.09, and the specific heat capacity of tea is same as water, 4.18. Heat of fusion, we just talked about in last slides, of water is 334 joule per gram. That's all the condition, and we can use this condition, the information, to calculate how many ice cubes needed to make the iced tea. Okay. Now we can do the calculation. First, we need to calculate the mass of the cup of tea. So we have 65 milliliter times density. Volume times density equals mass. So we have 65.5 grams of the tea. And then we can calculate how much heat will released. Okay, so when you convert the hot tea to iced tea, the heat must be released from the hot tea. Okay, because it dropped the temperature. So mass of the tea is 65.5. Specific heat of the ice, the tea is 4.18 here. And then temperature change, because final temperature is 0, initial temperature is 85, so you calculate negative 23,272 joule. You see if it's have a negative, that means it's exothermic process. That means this heat must released from this hot tea. Then it can be converted to iced tea. Now, how to absorb this much amount of energy? Ice, right? If you warm up the ice, you need energy. So you can use this energy to warm up the ice and melt ice. So now we don't know how many grams ice, right? But we know first there are two steps. Ice from negative 18 degree to 0 degree, that's a slope in the heating curve. If you remember our first slides, right? So the heat equation is mass times specific heat times delta T. Now second step is melt. Melt will be mass times heat of fusion. Now we can say, okay, I don't know how many grams of ice, but we can say X grams, right? So X times specific heat of the ice, 2.09 here, and then times temperature change. When you warm up the ice from negative 18 to 0, final temperature is 0, initial temperature is negative 18, and that is the heat to warm up the ice to 0 degree to melting point. Second step, second part is the heat need to melt this ice. So that's mass, we don't know how many grams, times heat of fusion. And then that total energy should equal 23,272. Now we can solve the X. Okay, now it's just mass, right? Okay, so X multiply 2.09 with 18, that's 37.62, and then that's 334X. Add these two numbers together, you get 371.62 times X equals 23,272. X will be 23,272 divided by 371.62. So you can calculate you need 62.6 gram ice. Now each ice is about 15 grams. So how many ice cube? So you can use the total mass of the ice divided by the mass of one ice cube. The division give you about 4.2 ice cubes. So if you add 5, that should be enough, right? Even 4 should be okay, right? So sometimes people don't want to make 0 degree iced tea, right? So maybe just 10 degree, that's okay. Okay, this is some everyday life issue, right? So now we have some idea. Now we have another type of question of thermochemistry is if you have a hot coffee and you just put some ice to the hot coffee, and you can calculate how much ice will be floating. So, right, if you add too much, then probably you don't need that much ice. So the ice will be left over and floating. So, of course, if you don't have enough ice, that will be all melt. So we have this question here. The given condition is a cup of coffee is the 210 around milliliter and 40 degree. So degrees Celsius. Density of a coffee is 1.19 grams per milliliter. It's higher than water. Okay. Single ice cube, same thing, right? About 15 grams, and the temperature is the same, -18 degree in freezer. And we add 9 ice cubes to this hot coffee. Okay, that's the condition here. We want to find out, is that enough or is that more than enough? Okay. Specific heat capacity of the ice is 2.09, same. Coffee, it's 4.18. That's the same as water, okay? Specific heat of capacity. Heat of fusion, same thing, okay? For water, it's 334 joule per gram. That's enough information now. First, we need to also calculate the mass of the cup of coffee. So the volume times density give you mass. Volume, 210. Density, 1.19. Make sure the volume or milliliter, and then you can calculate the mass, 249.9 grams. And then we can calculate the hot coffee to iced coffee. So from 40 degree to 0 degree, how much energy will released, how much heat released. Mass, 249. Specific heat capacity, 4.18. That's the same as water. Delta T, final temperature is 0. Initial temperature is 40 degree Celsius. So you can calculate that. Again, it's the energy released. So you have a negative sign here. So it's 41,783 joule. Now, we have 9 ice cubes. And we have 15 grams for each ice cube. So 9 times 15 is 135 grams ice added, right? So, and 2 steps again. For this 135 grams ice, you need to warm up, right, from -18 to 0 degree. So that heat will be mass specific heat of ice, delta T, 0 minus -18. So we can calculate, okay, to warm up this ice to 0 degree, you need 5,079 joule. Now you actually can compare this with the energy released. This is much less than that. So that means, yeah, the ice will melt. So how much heat left? So that is the heat released from the hot coffee. And that is the heat consumed by the ice itself, warming up from -18 to 0 degree to the melting point. So you have 36,704 joule. That is extra heat after warming up the ice to melting point. We have this much heat available to melt the ice. So we know the heat of fusion, we know the total energy, we don't know mass. But we can say, okay, X grams of the ice will be melt. So we can solve the X, just division, okay, 36,704 divided by 334. We can calculate, okay, 110 grams ice will be melt. Now, how many grams of ice we added? 135 grams. So how many grams left? Just do the subtraction. We have this much ice added initially. We melt 110. We have 25 grams ice will be left over. That will be floating on the coffee. Okay, so that's the answer of this question. We have one more example here. So that is another type of question in the thermochemistry. That is the question asks you the final temperature after you add a hot metal rod to water. Okay, usually that's water at room temp. This is a detailed question here. If the initial temperature of 45 milliliter water is 24 degrees Celsius, that's a room temp, what will be the final temperature of the water after 36 gram copper rod, which is 125 degrees Celsius, very hot, is added to this water? The information we need is density of water, It's about 1 grams per milliliter. Sorry. Specific capacity of copper is 0.385, and the specific heat capacity of water is 4.18. That's all information you need. Now, to solve this question, we need to find a mass of water of 45 milliliter. Since the density is 1, so it's actually the same number, 45 grams. And then assume the heat change only happened between the metal and the water, because actually you will lose some heat to the environment. But we assume we don't have that heat loss. Okay, so then we can, based on the first law of thermodynamics, the heat change of water and heat of change of metal, together total heat change will be 0. That means the total energy will not be changed, will be constant. Okay, so that's the first law of thermodynamics. Now, calculate the heat of water change. You need to use mass times specific heat times delta T. So, and we don't know what's the final temperature, right? That's a question. So we can say, okay, X degree Celsius is the final temperature. So then we can list these two heat. For water, it's 45 grams times specific heat capacity of water times heat change, temperature change. Final temperature X minus initial temperature 24, plus the metals heat change 36 is the mass of the metal, the copper. This is the specific heat capacity of copper, and this is the heat temperature change of the copper. We have a final temperature minus initial temperature is 125 degrees. That's 0. So we can solve the X. So from here, that's mass, right? Okay, just solve the mass, multiply this two number, and then multiply this two number. You can get this. And then you just multiply with this X and 24. You get 188.1X minus 4,514.4 plus 13.86X minus 1,732.5. That's 0. So, and do the more addition of this number, 188.1 plus 13.86, and that will be 202X. And this two number combined, that's negative 6,247. So solve the X. X will be 6,246 divided by 202. So final temperature will be 30.9 degrees Celsius. Okay, this is how to solve this kind of question. So if you have any question, please let me know. Okay, and good luck.